second session of our science and tech what we have done in the previous classes. Okay, and in the same way, let's I will go here peripherally, but I will also tell here in a deep also. You can watch this single video, you can get all the classes we map. Okay, let's dive in our class. We don't have to waste our wonderful time that given by God. Okay, what are the orbit? Now, first, what is the orbit? Orbit is the curved path followed by object. Here one is object. Just assume this is a Earth. Okay, see my cursor. Okay, it is moving like a circle, right? That circular path of a object to another object. Here one satellite, if assume if satellite is revolving around the Earth like that, right? Same, the curved path revolving one object around the another due to gravitational attraction. Some gravitational force is there. Okay. For example, just remember guys, moon around the earth, one example. In the same way, artificial satellite around the earth. We launch, right? Artificial satellite around the earth. In the same way, earth around the sun. Now, what is the center of mass? Center of mass, guys, you know, right? Actual, we launched a satellite will not revolve around the Earth. It actually revolve around center of mass. What is center of mass here? That is the whole weight of the Earth will lie in the whole weight of the weight of the Earth will concentrated one position, that is center. That position is the center of the mass. That is position is called center of mass. Okay, any object or any satellite or moon also, it is revolving around the center of mass. That's it. Uh, you can go it, you can read it, you can get. That is okay. I will read once. Satellite revolve around the earth. Actually, it revolve around the center of mass of the system. Okay, I said you know that only. Since earth is incredibly heavy, right? Earth is heavy, the satellite is super light. Yeah, satellite is super light. The center of mass lies almost inside the earth centers. The center of mass lies almost inside the earth center. You know, right? Now only I said that is the center of mass. Exception, if some exception also there. Okay, what is that? Some binary stars exist in our universe, right? Universe is huge, we don't know, it is infinite, right? In universe, the binary stars in the means same weight of the body will be present, right? Two different body will present. Just assume we have one earth, right? In the same, let's assume two earth and the universe, they revolve on their boundary. Okay, their boundary and their gravitational attraction, how much the capacity they hold, they will, but each other they will not revolve around each other. If one body is not revolve around the another body, and they will revolve themselves with this, they have some empty space what they exist. Okay, I think you can get. Okay, now what is the why orbit is stable? Yeah, some force will be exist, right? That force is centripetal force. Okay, let's why orbit will be stable. Anything moving in a circle. Yeah, orbit always moving in circle. Move in circle, right? We need an inward force, right? That is centripetal force. Okay, generally remember the centripetal force formula is the mv square by r. In a space, okay, in space, there is no physical string pulling the satellite. Okay, we don't have any physical holding that orbit to the satellite to revolve in a round. Okay, that's that the our gravity, the earth's gravity will provide that centripetal force. That our gravity providing centripetal force, that is mv, sorry, m, not m, here g, m by r square. Okay, when here now we are going to find the what is the orbital velocity. Means if we kept object in that orbit, that if in that orbit, how much how much the speed means, if we kept that object, how that object will revolve around the earth in a what speed. Okay, we are going to identify now. Okay, first we have to equate centripetal force equal to the gravity centripetal force. Then we equate, we get V is equal to square root of Gm by R. Here orbital velocity depends only on central body mass. Just remember guys, here orbital velocity depends only on central body mass. Yeah. Okay guys, now orbital velocity depends only on the central body's mass. Okay, I I already said center of mass, right? That's orbital velocity. It depends only on that central body's mass and the central body mass and height, that is radius. Okay, it does not depend on any satellite mass. Yeah, 1 kg satellite and 1000 kg satellite have a exact same speed in the same orbit. If 1 kg satellite will launch in the orbit, in the same way with 10 kg satellite launch in that orbit, both satellite will revolve around the earth in the same speed. They will not here we can't find any difference both of satellite, difference in the speed of both satellite. Okay, okay. Why will continue the when we launch the satellite, will satellite will not fall in earth again back. Why satellite, when we launch the satellite it will not come back to the earth. Okay, what is the reason behind it? That is because of its horizontal velocity. Okay, when gravity pulls it down, in the same way our surface curves away beneath it, so the satellite falls, but continuous horizontal movement make it constantly miss that earth gravity. Okay, always earth of the gravity always try to pull back to the earth of the satellite, but their that horizontal velocity of that object, it will constantly miss that path when the constantly miss the path of the gravitational attraction. UPSC concept, satellite is a stable in orbit, is in a state of continuous free fall. The Golden concept. A satellite in stable orbit is in a state of continuous free fall. Yeah, this is right, guys. Okay, some three critical cases is there here. First, when orbital velocity, not this, okay, that initial velocity, critical velocity. Okay, orbital velocity is less than the, okay, so sorry, orbital velocity not here. This is velocity of any our launch vehicle is less than the orbital velocity. Orbital velocity is square root of gm by r, right? Then what will be happen? Orbit shape what will be become? Okay, it is just remember launch vehicle velocity is less than the orbital velocity. It will fall back to the earth, guys. Okay, it will fall back to the earth because their speed is not compared to that orbit equal to that circular orbit, right? That's why the satellite will come back to the earth, and otherwise it will crashes, or or otherwise it will move in a suborbital. Okay, that launch is failed if the launch vehicle velocity and orbital velocities both are equal. It is a perfect circular. Okay, circular orbit also exists on it. That is stable and that is constant height and the speed is also same. In the same way, the launch vehicle velocity is greater than the orbital velocity. What will happen? It will become elliptical orbit. When launch vehicle velocity is greater than the orbital velocity, that's orbit shape will become elliptical orbit. Then it will become elliptical orbit when greater than the circular velocity, then which point we have to that launch point act as a perigee. Perigee means near to the earth. Okay, slightly below circular. Now, guys, that is where launching satellite velocity is less than that circular velocity. You know, right? Then what's happened? It again our satellite enter in a elliptical orbit. Okay, so here then launch point acts as the apogee. Here, what is the mean perigee and apogee? For Earth orbit, the perigee is nearest point to the Earth. Means here spin near to the Earth's surface. That orbital velocity or any satellite near to the Earth, it will its speed is maximum. The same way apogee that is farthest from the Earth, then speed of the satellite is minimum. In that for the same the Sun orbit. Okay, what is perihelion? Nearest point to the Sun. Perihelion means nearest point to the sun. Aphelion is the farthest point to the from the sun. The same. Here's some memory trick is there. If you want, go through it. Okay, Kepler's second law. What is that Kepler's second law? Okay, I will explain here. What is that? Let's see here. This is Earth, okay, and this is our elliptical orbit. Assume this is our elliptical orbit, and this is Earth. And okay, just we given time here. Just assume we given 4 hours. Okay, to to reach the satellite from this point to this point. Okay, we given 4 hours to reach this point to this. Our earth will sweep this much area. Okay, earth will our earth will not, that satellite will sweep this much area when we have kept 4 hour times. Okay, in the same way it is at the point of perigee. In the same way at the point of apogee, we again kept 4 hour same time. Okay, we are keeping same time, and again we are watching 4 hour. The how satellite will move from here to here, it will move. Okay, but covering them, that is sweeping the area here same as the this area. Okay, I think you get here. What is the when give a, that is a1. Okay, keep this is a1 and keep this is a2. This a1 divided by t1 is equal to a2 divided by t2. Here t1 and t2 are same, then they are cancel each other. A1 area is equal to a2. That's it. That is the second Kepler law. Okay, you can okay, I will only read here. A line joining the satellite to the central body sweeps equal area. Remember that? Body sweeps equal areas in equal interval of time. What is that? Now here some okay, some term. Okay, what is that? Velocity variation in elliptical orbit. Oh, what will happen now? Velocity variation in elliptical orbit is there. Appa. Earth gravity pulls harder when close. Oh, right. At the perigee, it is near to the earth, then gravitational force is maximum for that object. In that also, satellite accelerate perigee, but speed is maximum. Because of that, speed is maximum. The gravity pull is weaker when far from. Okay, the satellite decelerate at perigee. That's it. That is speed is maximum and speed is minimum. They are saying here. Apogee perigee. Guys, now some satellite motion, circular and elliptical orbit. The those only. Okay. Circular orbit exists in nature. Yeah, circular orbit, right? That is a round shape around the earth. Yes, but its proximity is extremely small. Our all satellite will enter in a elliptical. All not all satellite. Most of the our satellite will enter in a elliptical orbit. Just remember that. Okay, not all satellite. Some satellite also move in a circular orbit. I will tell you what the orbit will enter in the circular orbit in a later time. Okay, here almost very celestial body, little orbit. Okay, perfect circular orbit is highly precise ideal case. It requires exact launch velocity and perfect perpendicular direction. It need perfect perpendicular direction. We need to enter that orbit, and in the same way, exact launch velocity is same as that circular orbit velocity. Even a tiny cosmic disturbance. Some tiny cosmic disturbance means like solar wind or nearby asteroid. From the any asteroid, solar winds, you know, right, guys? Solar winds means like any some winds come from the sun. Okay, that heat wave. If from that also it is disturbed, from that also it is disturbed, then it will make its orbit in a that is orbit in a elliptical orbit, circular orbit to elliptical orbit. It will convert through with some cosmic disturbance, that is solar winds nearby asteroid. Next, rule of thumb here. Nature prefer elliptical orbits. A circular orbit is just a special case of an ellipse. Next, Kepler's law. I said you Kepler's law, right? And okay, that's it. Same, guys. This point is also same. That is perigee means near to the earth, and distance. Distance is minimum, speed is maximum. Okay, distance is minimum, but speed is maximum. But our topology distance is maximum, but speed is minimum. Just remember that also, and that relates the same concept to the sun also, but their term is we use perihelion and aphelion. That's it. Here there is no further. Okay. Here Kepler second law. I said already. Again it is repeating. This is this is same, guys. I said you that is elliptical orbit. That is the velocity is our velocity is greater than the orbit velocity. Then it will enter the elliptical orbit. In the same way, it is less than that orbital velocity. It is also again entered the orbital velocity. When less launching velocity is less than the circular orbital velocity, then the point of launch is apogee. Okay. For when it is greater, the launch velocity is greater than that orbital velocity, then its the length of launch is perigee. This is now that is some term. Okay, the speed and orbital period trend. What is that? Okay, let's dive in it to know to learn new things. Okay, we we know that orbital velocity, that is gm by r, that is orbital radius is r. Speed v is decreases when. Okay, let's go. What is that? Orbit 1. Orbit 1 is 500 kilometer versus orbit 2 is 20,000 kilometer. Orbit 3 is 36,000 kilometer. What is that? Now, then velocity 1 is greater than, its speed is greater than velocity 2, speed is greater than velocity 3. Speed is decreases when radius is increases, when distance is increases, right? In the same way, it is 36,000 kilometer. This is just 500 kilometer. So orbit 1 velocity is maximum compared to the orbit 2 and the same orbit 3. Orbit 3 velocity is minimum. Okay, I hope you get what I am saying. If you are not get, I will show again here. Let me. Oh, okay. This is one orbit. This is second orbit. This is third orbit. Okay. This is 500 kilometer. This is 10,000 kilometer. This is 36 Sorry, guys. This is 36,000 kilometer. Okay, this is near to that, and the same way this is compared to first one, second one is far from it. Both are near to that compared to this. Okay, when distance is increases, speed of the satellite decreases. Remember that. That's it. There is no further concept here. Oh, oh, okay, that only. What will become the period? Means some period is right, some period is right. Okay, Earth will revolve around the sun in a 365 days. Right, Earth will revolve in a 365 days. In the same way, what will happen like that in a distance or in a period? What will be that time taken to complete one full revolution? That is orbital period. Okay, when radius increases, velocity decreases. Here we read. In the same way, distance increases, right? Distance increases. Then time period also increases. When distance increases, time period also increases, radius increases. But velocity decreases. Just remember that. And assume by yourself in a space. 10th floor, radius increases, velocity decreases, again circumference increases, the period increases. That's it. Okay, here what is some is there. Okay, approximate values in the exam. Okay, that is orbital altitude and their period, time period, and classification of the orbit. Low Earth orbit, medium Earth orbit, GPS satellite, and geostationary orbit. Let's go. Low Earth orbit will be called low Earth orbit when it is from 400 to the 500 kilometer when it is stay. That's time period is the 90 minutes. Just remember that is 90 minutes. 400 to 500 kilometer. It will complete one revolution in a 90 minute. Okay. Low Earth orbit. We kept any satellite in a low Earth orbit. That satellite will revolve around the Earth in a 90 minutes. Just 90 minutes. Okay. That is around 1.5 hour. 1.5 hour. That's it. When we kept satellite 200 kilometer above, then time period is 2 hours. Here that is medium earth orbit. Just remember medium earth orbit. It will take 2 hours and their altitude is 2000. Oh, now is 20,000 kilometer. 12 hours. It will take half a day to orbit. Revolve around that earth. That is GPS satellite. GPS satellite will take half day to revolve the earth. Means in a whole day it will revolve 2 times. Now 360 kilometer, 24 hour it will take. That is geostationary orbit. Just geostationary orbit. When we kept any satellite at the geostationary orbit, it will take time. Its time period is become 24 hour, and we will launch the geostationary orbit at the 36,000 kilometer. What is solar system role here? Planets further away from the sun move slower and take much longer to the revolve. The same, right? Just remember solar system. Mercury, Mercury will revolve speed, and then Venus, and then Earth, and then Mars, Jupiter, Saturn, Uranus, Neptune. Here distance increases, right? But speed of the all the planet decreases with respect to their previous planet. And the same way, time period increases. Yeah, its time period is very huge compared to the Mercury. The moon example. Distance of the moon from the earth is 3.84 lakh kilometers. Very large orbit radius is. Its time period 27.3 days. Oh, our moon will revolve around the earth in a 27.3 days. Commonly approximate 28 days in a simple problem. Okay guys, that's it. Some space debris hazards warning is there. What is the space debris means? The because orbital speed are incredibly high in a low Earth orbit. Low Earth orbit, the orbital speed is high. Even a tiny point particle carries enormous kinetic energy. Okay, in low Earth orbit, single tiny point also will carry huge kinetic energy. When it collide, it behave like a bullet. Wow, wow. Just assume, guys, here when they will collide each other, it behave like a bullet and can cause severe damage to spacecraft. Why can't satellite orbit very close to the Earth? What is the reason here? Why satellites orbit very close to the Earth? Why any satellite orbits where why it is not there any orbit near to the close very close to the Earth? Why? Because of our atmosphere. Okay, if no atmosphere on the Earth, if we launch a satellite 1 kilometer above the Earth, then it also revolve in a perfect circular motion. Okay, and for but in real case, what is there? Our Earth has atmosphere, right? Because of that atmosphere, in reality, Earth atmosphere create a severe air drag, that is friction, and because of that friction, reduces orbital speed and drains kinetic energy also. It will reduce kinetic energy and reduce orbital speed and cause the orbit to decay from circular to an elliptical spiral. It will also cause if we launch any satellite in a circular orbit that if because of that friction then circular orbit to it will turn elliptical spiral. The force atmospheric re-entry when the satellite eventually burns up due to the friction. That's it, guys. The critical altitude threshold, and that is you can go through that. And now classification of the Earth orbit. You have read, right? That is low Earth orbit, medium Earth orbit, geosynchronous orbit, and high Earth orbit. You know the height, right? That is 160 kilometer to 2000 kilometer. That is low Earth orbit. It will take 80 minutes to or 90 minutes and up to 2 hours. It is 2000, right? So typically it is 90 minutes, but its distance compared to the distance that is 160 kilometer, it will take 80 minutes. For 2000 kilometer, it will take 2 hours. For medium Earth orbit, 2000 kilometer to 35,786 kilometer, it will take approximately 2 hours and to 24 hours also. And also geosynchronous orbit, that is exactly 35,786 kilometer, exactly 24 hours, that is a side real rotation. High Earth orbit, that is above 35,786 kilometer, greater than 24 hours. You can hear that is low Earth orbit, this is medium Earth orbit, geostationary or geosynchronous orbit. This is okay. It will take 24 hours, it will take 12 hours, it will take 90 minutes. Now, low Earth orbit, deep dive. Okay, let's go. What is that? Its range is, its altitude is no, we know, right? 160 kilometer to 2000 kilometer. Its highest orbital speed, yeah, it is very close to the Earth, then its orbital speed is high. The lowest time period, yeah, it is very close to the Earth, hence time period is less. Closest to the Earth, right? Why use low Earth orbit? Closer distance require less energy to send signal. Obviously, it required less energy to send there and send signal also. Provide much higher photography resolution and minimize communication latency. Latency means some delay happening in delay in a communication. Okay, it will minimize that latency also, communication latency also. When we launch the in a satellite in a low Earth orbit, benefit from that. Why? What are the uses? Okay, we need less energy and less fuel to keep that satellite, and it will send the signal very easily, and it will higher photography resolution. We can see clearly whatever there in earth, and minimize that communication latency also. Main low earth orbital application, it's earth observation, that is remote sensing, used to forestry, mapping, and disaster management and agriculture. It is closer orbit means sharper image. Just remember, it is closer to the orbit. It can give very sharper and clear images. So remote sensing, remember low Earth orbit. That is forestry mapping, disaster management, like etc. And for example, the Indian satellite like Cartosat and OceanSat, resource resources sat, sorry, resource sat, resat, all are the example of the remote sensing orbit. Cartosat, OceanSat, resource sat, resat. Now, second one is human space flight station. The lower radiation risk and easier safely access make low Earth orbit the default home for space station. Yeah, our international space station is also there in the low Earth orbit, and the Tingong, it is it, it is also space station of China, and Gaganyaan, India's upcoming mission. You know, right? Gaganyaan. Right, it is human space flight. Okay, International Space Station also there. Not only Apollo lunar mission went behind low Earth orbit. Okay, Gaganyaan means we can launch the our human being on there, and high speed satellite internet. Wow, wow. The traditional satellite internet had huge delays. Traditional satellite internet had a huge delay, right? We can often heard that the modern constellation use low Earth orbit to keep communication latency minimal. The great for gaming, video calls, and real-time remote surgery. Starlink example, Starlink OneWeb. Just remember these are high latency internet. Okay, these are satellite. Starlink OneWeb satellite are help help us to minimize the latency and keep our communication in a speed manner. Starlink OneWeb. Okay. Sun synchronous polar orbit. What is sun synchronous polar orbit? This is one of the most practical and frequently tested orbit in Earth orbit. Sun synchronous polar orbit. What is a polar orbit now then? Hmm? Satellite orbits from North Pole to South Pole and back, and crossing the equator perpendicularly. Inclination angle is close to 90 degree, typically 97. Okay, this is equator. It will revolve like this. This assume this is Earth. It will revolve like this polar orbit, and it is perpendicular to the Earth. It is perpendicular to the equator. Sorry, right? Then that's why its inclination. That's its inclination angle is approximately 90 or 97. That is polar orbit. Okay, the sun synchronous orbit is a special polar. It is also, just remember guys, here sun synchronous. It is also special polar orbit where satellite passes over any given location on the earth. It exact same as local solar time in every single day. It has same local solar time. It will look as every day, same point, same time for every day. If it crosses Delhi at 10:30 a.m. today, then it will cross Delhi at 10:30 a.m. tomorrow also. Okay, I hope you get. What is the identical solar timing so valuable? The identical lighting condition means shadow match perfectly 1 a.m. This makes tracking physical changes on Earth highly accurate. Comparing deforestation, glacier melt, urbanization rate between 2005, 20 and 25. Why most the orbit rotate? Precision. What is that precision? Earth rotates and travel around the sun, right? Earth rotates and travel around the sun. The satellite orbital plane must also slowly twist, that is orbital precession, at approximately 360 per year. Without this, the local crossing time would slip. Okay, okay. Secret rule of Earth shape, that is ablanteness. Just remember here, secret rule of Earth shape, that is ablantness. Okay, let's dive what is that ablantness. Earth is not a perfect sphere, right? We know Earth is not a perfect sphere and it is an oblate spheroid, right? Fat at the fat at the equator, not it is pole. Okay, it will pole. Just strike out this, okay? That is pole. This equatorial bulge exert an uneven gravitational. The uneven gravity naturally and beautifully rotate the orbital plane just enough to keep it sun-synchronous. Sun-synchronous orbit are naturally possible on bulged planet like Earth, Mars, but not on Venus. Okay, bulged planet. Sun synchronous orbit is possible for Earth and Mars because they are so bulged planet at the equator. It is not the sun synchronous orbit. It will not possible for the Venus because it will not has bul. Okay, bulged planet, bulged like shape. The Venus is almost perfectly spherical. Lack of required gravitational bulge symmetry. Launch vehicle connection. The India's legendary rocket, that is PSLV, Polar Satellite Launch Vehicle. You know, guys, our MOM mission, that is Mars Orbit Mission. You know, right? We achieved that we achieved that mission through this satellite only. We g- we have gone through in a less fuel, in a less in a less fuel and very first attempt we have achieved to go the Mars. Okay. The originally designed specifically to inject remote sensing satellite, it's specifically designed to just to go low Earth orbit or sun to sun synchronous orbit, polar orbit. Just inject remote sensing satellite to into the sun synchronous polar orbit. It is polar satellite, so polar orbit has to need to inject on the orbit. Okay, that is polar name. That's why that polar name is there. Now medium Earth orbit. Medium Earth orbit. Its height range is 2000 km to 35,786 km. Its core application is global navigation satellite system. Just remember, its core application is help. Its core application is to help navigation satellite. Okay, what is why use medium Earth orbit for navigation? Why we can use that only? Okay, it provide as much longer coverage footprint than low Earth orbit. It provide more coverage area than low Earth orbit, and meaning you need fewer satellites. Okay, we need here less satellite to cover Earth, but and keeps latency and transmission power requirement as much lower than the geostationary Earth. Typical GPS orbit altitude is 20,200 km with a period of exactly 12 hours. Navigation system, country or agency. Okay, GPS is belong to US, right? And orbit type is medium Earth orbit. GLONASS, it is belong to the Russia. It is also medium Earth orbit. And Galileo, European Union, it is also belong to the medium Earth orbit. And Baidu, it is belong to the China and it is also mainly kept in medium Earth orbit. And some GSO, geostationary orbit. NAVIC, IRNSS, it is India's. Okay, It's our Navic global navigation satellite system. Our India says that is Navic. Okay, India. That is kept in geosynchronous orbit or geostationary orbit, not medium earth orbit. Just remember, our Navic system we are not kept in medium earth orbit. We have kept in geostationary. What is now? Now we are going into the geosynchronous and geostationary orbit. Its altitude is 35,786 km above Earth's surface. Physical rule. What is here? Okay. Its precise height and time taken for a satellite to complete one orbit matches. Now, geosynchronous and geostationary orbit. Okay, its altitude 35,786 km above the Earth's surface. Its physical rules. What is that? Its precise height and time taken for a satellite to complete one orbit matches Earth sidereal rotation period. Exactly, that is 23 hour 56 minute and 4 seconds. Okay, that when we kept our satellite in a geosynchronous geostationary orbit, its time period, it will take time, that is exact Earth revolution, right? So Earth sidereal rotation, that is 23 hour 56 minute and 4 second. Here some condition also there for geostationary orbit, that is ge- just remember here guys, geosynchronous orbit, it is circular orbit. I said in the earlier, geosynchronous to some circular orbit is there, right? When we launch the satellite in a geosynchronous, it is a circular orbit. Okay, it is exactly at 35,786 kilometer, and most revolve in the same direction Earth spin. Here, Earth will spin in from west to east. Okay, Earth will rotate from west to east, right? In the same way, the our launching satellite also will move in a west to east. Both are same. And okay, let's go with this also. The many students think they are identical. Both are identical, huh? Everyone will think thought like that, huh? So what is the difference? Now we can enter. What is the difference between geosynchronous or geostationary? Okay, at any orbit with a time period of 24 hours. Okay, but orbit can be tilted here, inclined or elliptical. It is also some are elliptical or it is inclined angle are there compared to the equator. Okay, from Earth, a geostationary orbit, geosynchronous orbit satellite is not fixed. It rises and falls, tracing a figure eight analemma path is a sky daily. Figure eight tracing a figure eight analemma path in the sky daily. Geostationary orbit, it is special and it is a strict subcase of geostationary orbit. The orbit is perfectly circular. This orbit is also a circular. Okay, just remember this orbit is also circular. Both are circular, but it is zero inclination towards the equator. It is completely same lie and the parallel. It will be parallel to the our equator, and meaning it sit directly above Earth equator. From Earth, it appear 100% stationary at one fixed spot in the sky, perfect for satellite TV dishes. Some comparisons of the Earth orbit is there. If can you want? Can I go with this one also? Okay, let's go. It I will take ASP. Okay, height is to up to 2000 kilometer and medium height is 2000 to 35,786 kilometer, and it is exactly 36,000 approximately, and higher orbit above than the 36 kilometer 36,000 kilometer. Its speed is highest because it is very near to the earth. It's moderate and it's slower and it's also lower speed. speed is over. Next time period is 92 2 hour. Here 2 hour to 24 hour. It is exactly 24 hour geostationary geosynchronous orbit. But higher the orbit is greater than the 24 hours. And coverage, it will cover small, and it is medium, it is very large, and it is largest. Latency, it is very lowest, and moderate, it is highest. Main users: Earth observation, international satellite station is there, satellite internet, navigation, GPS, Galileo, GLONASS, weather monitoring, TV broadcasting, deep space tracking, and polar science and deep space tracking. Weather monitoring and TV broadcasting, they are kept in the geostationary orbit. Our navigation satellite is also there in geostationary to geosynchronous orbit. Okay. Now, Earth observation satellite in geostationary orbit. Yes. Yes, while remote sensing satellite usually prefer low Earth orbit, right? It is very close to the Earth. So weather observation satellite, it must be placed in where? Geostationary orbit. You know, right, guys? Here, where it is gone. See, geostationary Earth orbit and geosynchronous orbit. These are weather monitoring and TV broadcasting, right? That is also that only here I am saying the weather observation satellite is must be placed in geostationary orbit. It allows them to stay continuous at one region, example matching India's storm pattern over the 24 hour without break. High Earth orbit with an altitude greater than 35,786 km, that is approximately 36,000 km. Due to extreme distance, its communication return to the Earth, it become very low, so has it has high head latency, and lack of communication will happen. So it and the high Earth orbit is used just to know very deep search in astronomy, or can any scientific research have to need to conduct means they can use high Earth orbit. The coverage math of geostationary orbit. Okay, it is approximately 36,000 kilometers. A satellite line to cone spread wide over the globe. One geostationary orbit satellite can cover approximately one third of the Earth. Okay, here one we this is a satellite. Yeah, assume it will cover 120 degree. When 120 120 into 3 is 360, right? The same way, we need three satellite to cover whole Earth. When we launch the satellite at geostationary orbit, we can just need three satellite to cover the whole Earth. The exactly three satellite placed at 120 separation. Okay, what is the polar exclusion? Even within three geostationary orbit satellite, the extreme north and south pole are never covered. Oh, with these three satellites will cover the whole Earth, but north and south pole it will not covered. Why? What is the reason? Because geostationary orbit directly over the equator. Okay, we kept geostationary orbit. Okay, it is parallel to the, see, this is just assume this is orbit. Okay, just imagine the satellite are revolving like this. Okay, not like this, because geostationary Earth orbit directly over the equator. The plane tribal blocks line of sight to high altitude. High altitude region must use highly elliptical orbit. And okay, now let's go advantages of geostationary orbit. What is advantage? It is continuous link, means constant connection with zero signal tracking needed at ground terminal, and the wide coverage footprint. Wide coverage footprint is there. Just three satellite is there to cover whole Earth. It is long lifespan. Yeah, because we directly placed it parallel towards the Earth, but its high altitude is high, but parallel towards the equator. Okay, that's why and equator and its rotation and earth rotation become equal, and earth will also rotate from west to east. The satellite also rotate from west to east. The disadvantage of geostationary orbit, it is no polar coverage. It will not cover polar because it will not revolve like the north to south, south to north. It will not revolve like it just revolve west to east. High latitude polar zone fall outside. Okay, high latency because delay it will be there. High launch cost, raising a heavy satellite to 35,000. It will need some more fuel to launch, more fuel compared to the medium earth and lower orbit. Highly elliptical orbit, that is Molinian orbit. Unlike circular orbit, a satellite is in a highly elliptical orbit continuously alter its speed. Okay, wow, wow. It's it is highly in elliptical orbit. Okay, it continuously alter its speed. It will change its very closest at the Earth, and its fast speed is the fast. When at when satellite at the opposite, it is fastest, right? Slow is the speed. Let's satellite hang over a high altitude polar region, Russia and Canada, near apogee for hours, acting as a quasi stationary terminal with equatorial geostationary satellite can't reach. Okay, now what is that? Orbital speed and velocity change. Orbital speed and velocity change, I said you in the earlier. Okay, okay, let's. It is one of the important topic. Okay, that is Human transfer orbit. What is orbit transfer? Human transfer orbit. What is that? What is this? Yeah. How do we know? How do we move a satellite from an initial low Earth orbit to the final geostationary orbit? Use an intermediate. Okay. We cannot directly launch a satellite directly from low Earth orbit from Earth to the geostationary orbit. We take the help of low Earth orbit, medium Earth orbit. Okay, that intermediate path and fuel efficient elliptical path. When we entered in, okay, just assume here. Okay, it will perigina, it will opposite. When it will revolve like this. Okay, one round is complete. Just assume it is lower orbit. Okay, when it is lower orbit. Okay, when we burn the engine again, it will again shift in the another orbit, that is medium earth orbit. Just assume like that. Okay, and again burn the engine again, engine thrust will open, then it will enter, it will need to enter in the geostationary orbit now. This after when the here to here, when entering geostationary orbit, that path is Hanuman transfer orbit. Okay, let's see. Satellite is placed in a circular orbit. Okay, first satellite is placed in the circular orbit. Okay, again, then first speed increases, first will burn and speed increases. Satellite enter in an elliptical orbit. Then when first we burn, when it is first we entered the satellite in a circular orbit. Then first burn is happen. When first burn is happen, it is enter in the orbit elliptical velocity. Okay, entering the orbital velocity, elliptical transfer orbit, the apogee reaches exactly there. And elliptical orbit, who reaches when it reaches here, when it reaches here, the satellite costs to apogee. Its speed is lower than required circular Earth. Here speed is very low. Okay, compared to the here, because it is opposite point. This perigee. And to burn a apogee engine again, fire second speed increase orbit circularize into geostationary. When here burn again, it is in a elliptical orbit now. When second burn, when engine thrust will be open again highly efficiently, then it will move in a circular orbit. Okay, that is geostationary orbit. That's it. And quick revision of there is there here low earth orbit, then elliptical human orbit, and then geostationary orbit, how it will went. And these are some important points are there, those common word only. Okay, some points related to the geostationary transfer orbit. Okay, it is one of the orbit, that is just a stationary transfer orbit. What is geostationary transfer orbit? What is it? Yeah. Okay. Then let's dive to learn it. Okay. Yeah, highly elliptical orbit. It is highly elliptical orbit. Okay. It's very highly elliptical orbit like this. Okay. And used as an intermediate step. Okay, it is used as an intermediate step. Here guys, how means, okay, I said the in a before class, right? When satellite is launched in a circular, that is low Earth orbit, in a circular orbit, okay, then we have to launch in a that is geostationary orbit, right? To launch the satellite in a geostationary orbit, that is also circular orbit, right? For that, we need uh, one elliptical orbit. Okay, that is uh, that is called here, that this elliptical orbit is used by this elliptical orbit is used this orbit is the geostationary transfer orbit. I hope you get. Okay. There is no another concept here, there is no complex concept here, just do here. It is the first circular orbit. Okay, it is circular orbit. This is second circular orbit. Okay, the satellite launch from here to here. Okay, we need to move satellite from this circular orbit to this circular orbit. For that, we need this elliptical orbit. Okay, this intermediate elliptical orbit is the geostationary transfer orbit. We use it on a intermediate step to transfer payload from low earth orbit to into the geostationary orbit. That's it guys, it is the intermediate orbit. Any no other complex topic here. Okay, okay, what is that here now? Core engineering principle, what is that here? There is no complex here, just just go through once what is the important things will be there here. Heavy launch vehicle rocket do not directly drop a satellite into its final 35,786 km geostationary orbit slot. Doing so require impossible amount of fuel and massive rocket stage. Okay, l- when we launch the when we launch the rocket from the Earth, remember, from the Earth, we do not directly launch in a geostationary orbit. That's it. We If we do like that, it will require massive amount of fuel and energy we need, and rocket stages also we have to develop very highly standard, but that is not possible because it is very expensive. We have to uh, keep our dependence on the fuel and our expensive material, so we have to reduce, that's it. And yeah, it will take some time when it enter in a elliptical, and it will enter in but definitely one day it will enter in a geostationary orbit now, in a less amount of the fuel and some minimum what we have the now PSLV GSLV rocket, we can go through that. Now instead the rocket places the satellite into geostationary orbit. Here perigee apogee, you know, right? And this satellite then use its own onboard liquid apogee motor. Okay, onboard liquid apogee motor thrust to circularize, and when satellite it will be reached in the apogee, right, apogee point. Then again here we burning the thrust at the second point, it will burn again to enter the circular orbit. Okay, if we not thrust our engine highly, then it will revolve in a elliptical orbit. So we give if some force energy give to revolve that circular orbit. That's it. And why use geostationary? No, geostationary transfer orbit. Yeah, geostationary transfer orbit. Save massive amount of rocket booster fuel. It will save massive amount of rocket booster save. And allow smaller, highly inefficient vehicle. It will allow smaller, highly inefficient lunar vehicle. And now, what is that? Spacecraft speed and orbital dynamism. What is that? You have read this, right? Circular orbit speed that is equal to that launch vehicle speed is equal to the orbit circular speed. Then it will become a circular path. Orbital velocity, you know, right? Orbital velocity is equal to the launching vehicle velocity. Then it that launching satellite will enter into the circular path, you know, in the earlier. In the same way, elliptical orbit speed, yeah. Here, what is that? This velocity is greater than orbital velocity. If any other launching vehicle velocity is greater than orbital velocity, then it will enter in a elliptical orbit, but launching point become what is apogee. Okay, launching point become apogee, and it is also in the elliptical path. When it is okay, now this is what happened. Okay, now escape velocity. What is this escape velocity? Or okay, threshold speed at which kinetic energy of a spacecraft matches its gravitational potential energy, allowing to break free forever. Means some boundary is there. Now we have to escape from our gravitational force. After that, anything will be the present in the space that will flow in anywhere like that. Just we have to pass that boundary. Here escape velocity deep dive from the surface to earth. Stella, from the surface to earth, escape velocity evaluate to like this. Okay, from the surface to earth we have to move. If we need to cross our escape velocity boundary, we need to cross this much, 11.2 kilometer per second. Oh, our launching velocity have to keep 11.2 kilometer per second. We need to escape from the gravitational attraction. And here that is those concept only you can read. If you want read, pause this video and just read once. You can get a knowledge. Aerobraking mechanics. Using a planet atmosphere drag friction to reduce the orbit size of a spacecraft, bypassing the need for huge deceleration fuel burns. What is that aerobraking mechanics? What is that? Means when planet, yeah, in okay, just remember, Earth has an atmosphere, right? And it has some wind, flowing wind in the upper in altitude, high altitude, and some friction will be there. So that will that will reduces the orbit size of the spacecraft. So for that we need huge deceleration fuel burns. For that we need fuel more. That is the aerobraking mechanics. That's it. There is no huge complex topic here. This just need to break that air phase of the space phase. I am saying okay, air phase. What are them? Okay, just remember it is atmosphere, right? Okay, it is Mars, and Mars is also atmosphere is there. Okay, we need to cross that atmosphere. We need to burn some more fuel because of the friction. that is that aerobraking mechanics. The spacecraft orbit is initially highly elliptical with an apogee far out. At perigee, the spacecraft skim the very upper and thin layer of the planet atmosphere. And then atmospheric drag slows the vehicle. Perigee, the spacecraft skim the very upper and the thin layer of the planet's atmosphere. Atmospheric drag slows the vehicle, which naturally lowers the apogee height and the next loop. Okay, and then repeating this pass several times, the orbit circularizes into the target altitude without firing engines, where it is used primarily around target bodies with atmospheric like Mars and Venus. We use these mechanics at the planet of Mars and Venus because they has atmosphere. Okay, now one of the interesting point we are coming to know how Chandrayana Mangalyana reached destination orbit. How they will reach on that. Okay, instead of launching directly on a straight path to the moon or Mars, ISRO implemented a highly economical step-by-step orbital rising maneuver. Okay, now step by step trajectory strategy. What is that? Okay, how the satellite will reach orbit of the Chandrayaan or Mangalyaan? How? Okay, let's go to it very. Please concentrate here. Okay, when you are studying it, please concentrate. How the satellite will launch the Chandrayaan? Okay, okay. The rocket drops spacecraft in an elliptical low Earth orbit. Okay, first, from the Earth, from the Earth we drop the rocket at the low Earth orbit, okay, in a elliptical orbit. Again, orbit rising perigee burns. Here, at the position of the perigee, we burns the engine thrust and then it will again enter in the another elliptical orbit. In the same way, okay, closest to the Earth, that is no, and on broad engine fire, the speed increases, stretching that apogee out further. That's it. Then okay, then it will enter in the another elliptical orbit, right? After that, here what is the translunar injection? What is this? Okay, after several burns, apogee reaches Earth gravitational escape boundary. A small final speed boost escape Earth gravity. Here, okay, this is the when satellite reach this apogee point. Okay, after that, when it come again at the point of apogee, okay, then further they will further fire the thrust of the engine, then it will enter, then it will enter in a, okay, that is lunar transfer path. Okay, when it will, okay, sorry, from here it is not, when it will come apogee at the point when we burn the thrust of the engine, it will enter them, it will escape the escape the earth gravitational force, and then it will move that another body's orbit. Okay, then it will revolve like that. And after that, capture and braking the moon's gravity capture vehicle. After when, let me show. Okay, when enters the satellite here, when we burns the engine thrust, right, then it will, okay, it will like that now, it will coming like that, and we burn, then it will go like this and enter in the sorry, like this, and this is the moon, just treat like that, this is moon. Okay, wait 3 minutes. Okay, satellite going from like this, and when engine burns and thrust will increases, and then it will enter another atmosphere's orbit, that is, and that is moon's orbit. Okay, then it will start, and at one point it will become stable. This is our moon. Okay, like that will go satellite, that is, and then capture and breaking the moon's gravity capture. When from escape from here to, it will capturing this orbit, capturing that orbit. When we capture this orbit, that is only, and there is no engine fire in the reverse, means, okay, we burns in a highly. Okay, now here what will happen, we need to slow the speed of the burning thrust, stepping slow down and ellipse to be stable circular lunar orbit. That's it. Okay, here special terminology is there. Orbit around other bodies. Okay, what is that? Okay, some terminology you know in the in the earlier. Perigee means near and speed is maximum. Apogee means farthest from the. Oh, sorry. Yeah, that is correct. But yeah, this is right. Nah. Means R means distance, right? Radius. I thought here velocity that. Not. Okay. It is right. Apogee is farthest from maximum distance is there, but speed is minimum. But moon, it is perilune and it is upper lune. And the Mars, perihelion and apohelion. For sun, it is perihelion and aphelion. That's it. Okay, why rocket are launched from the east coast? Why most of the rocket? Just remember, guys. Why most of the rocket will launch from east coast? Why not from the west coast? This is not. All the rocket will launch from east coast. That is not true, because some of the launch vehicle will also launch from the west. I will tell you that. Okay, what is that? Rotation. First reason is the rotation boost and drips fall safely. What is that? Earth spin from. Okay, Earth will rotate from the west to east. For that direction, when we launch, just just treat this is west. Okay, this is east. Okay, Earth will rotate from west to east. Okay, if we launch from here, then our launching vehicle capacity will increases. Okay, the launch eastward allows the rocket to piggy back on the earth rotation speed and saving the tons of fuel. We can save the because of this we can save the maximum fuel waste. Next, debris fall safety. The launching from the east coast ensure that if launch fails. Okay, this is our India. Okay, this is our India. Always we launch from Sriharikota, right? From the east side, not west side. Okay, if our launching vehicle failed, then most of our rocket debris will need to fall in the sea, not in a land area. If we launch in the west side, then our if rocket is failed, then it will fall on the populated land. That's why we have to prevent, because women's life is very important. That's why we have to launch from the east coast. That's because of that the launching vehicle if failed, it will fall on sea, ocean. Why launch near the equator? Why we can launch near the equator? Yeah, right. Our India is like this, right? Just imagine. Don't imagine. I will draw here. We will not launch from anywhere here. We launch here because just remember this is whole earth and this is equator passing. Okay, this is equator. This point is near to the equator. So why launch near to the equator? What is the reason? The earth linear rotational speed is maximum at the equator. Okay, earth linear rotational speed. Linear rotational speed is maximum at the equator. In the same way, to drop to zero at pole. In this pole, it will the zero speed. The equatorial launches maximize the payload efficiency. It helps that payload efficiency will maximize and make insertion into the flat geostationary and geosynchronous orbit planes much simpler with a minimal plane change in adjustments. For example, Sriharikota is India and Cape Canaveral, that is USA, and Kourou, that is French Guiana. Some note is there. Israel launches. Yeah, I said some satellite will launch from west side also. Okay, this is west side and this is east side. Okay, launch and yeah. Just assume this is Mediterranean Sea. This is Israel. This is Lebanon. This is Jordan. Some countries there, right? Here, not all nation launch eastward. The Israel launches its Soviet rocket westward over the Mediterranean Sea. I said right, Israel it will launch like that from west side because if the mission is failed, then that launching debris will fall on the ocean Mediterranean Sea. That's why. Here something okay, what is that sounding and orbital rocket? What is the difference? You have to know this sounding rocket and what is orbital rocket. Okay. Okay. What is sounding rocket? That take sufficient payloads to upper atmosphere layer and collect data and drop back in a suborbital path. They do not go to the orbit. What is orbit rocket here? Carry enough speed to the put satellite into the stable and permanent circular or elliptical path. You have got difference, right? The scientific payload to upper atmosphere layer collect data and drop back into the suborbital path. It do not go to the orbit. Okay. Indian spaceport and launch dynamics. Okay, now Indian spaceport and launch dynamics. Or it is Satish Dhawan Space Center, right? Satish Dhawan Space Center. It is there in Sriharikota, Andhra Pradesh. It's India's primary spaceport. It is India's primary space sport and houses launches for PSLV, GSLV, LVM3 and SSLV. The Kulasekharapattinam spaceport is present in the Tamil Nadu. It is still under construction. Okay, developed primarily to support small launch vehicles. Here, what is that? Dog leg maneuver issues. What is this? When launching southward into polar orbit. Okay, when launching into southward into polar orbit from Sriharikota, rockets must steer around the island of Sri Lanka to prevent flying over populated territories. Okay, when we launch the rocket from Sriharikota, it might have a chances to fall on the Sri Lanka. When the mission is failed, then has some minimum chance, some chances it will be there to fall on the Sri Lanka. They that's why they trying to bring that in Tamil Nadu to overcome that issue and consume massive fuel and reduce that rocket satellite lifting capacity. Kaleshkara advantage. What is its advantage? Okay, since it sit further south, again it will become south. Okay, rockets can launch straight southward with no obstacle. Here there is no obstacle, and we easily can launch the satellite, saving critical fuel and boosting performance. We will save our fuel also, and also we can build performance also. Sorry guys. Okay, now what is that? Is Tumba Equatorial Rocket Launching Station? What is that? Okay, guys. Here also it is located Thiruvananthapuram, Kerala. Established in 1963, it is India's first launch pad. It is India's first launch pad, Thiruvananthapuram. It is present in the Kerala. Okay, why Tumba? It is needed for us. It directly on the Earth magnetic equator and making it uniquely situated for studying the ionosphere and upper atmospheric electrojet. Here, example, but it lies directly on the magnetic equator. Okay, it directly like one reason it is present at the Kerala, that is equal to that magnetic equator, and making it uniquely situated for studying the ionosphere and upper atmospheric electrojet. In the same way, it is crucial for exam fact. Okay, what is that? That is Tumba Equatorial Rocket Launching Station only launch. It will only launch sounding rockets for weather and atmospheric research, not large orbital rockets. The Tumba Equatorial Rocket, it will never launch any large orbital rockets. It just launch sounding rocket. Why rocket use multiple stages? Why single stage rocket would have to carry its massive empty metal fuel tanks all the way to orbit? By dividing the vehicle into multiple stages, the rocket discard empty tank so as they run dry. This shared dead weight and drastically boosting structural efficiency and final velocity. Because why it is multiple stages means multiple stages is there when its fuel is over, where when the fuel is the stages of the fuel, solid, liquid, and solid liquid for the PSLV, right? In the same way, when solid fuel is over, the tank will be remain. That tank is made from the iron. That has to be, if that we have deleted, that's the rocket weight is become rocket weight become reduced. Okay, because of that we have to because of that we have to uh, divide that rocket in a multiple stage. Just we want to reduce the weight. Rocket physics, gravity gradient, and multi-staging. Okay, what is this about? Okay, what are the gravity gradients or multi-staging of the rocket? What is it? Okay, the gravity versus distance relationship. Let us assume gravity. The gravitational attraction on rocket of mass m decreases exponentially at its climb. When rocket go up, go up, its gravitational attraction will become reduces. Near the surface of Earth, gravity is maximum. Just remember that near the Earth, gravity is maximum, and then rocket need the rocket is packed with the fuel, right? Rocket is packed with the fuel and require maximum thrust for the initial stage. At high altitude, the gravity drops. Okay, at high altitude, at high height, the gravity becomes low. That's inverse square law. And if r doubles, if r is doubles, the force drop to 1 by 4th, and if r is increases 1 by 36. Okay, here there is no nothing. When height is increases, gravitational attraction will be decreases. That is inverse square law. Okay, and that here core concept is the higher altitude require significantly less thrust. When reach that higher point of the set higher point height, maximum height, then we need very less thrust because the local gravitational pull is weakened. That's it. There is no more detail on about that. Okay, now why not use one hug engine. What is that? Stacking mandate. Okay, let's see. What is this? I also don't know what is this. Okay, let's go to learn what is this. Dead weight penalty. What is dead weight penalty here related to the racket? Okay, carrying a massive engine structure and empty fuel tanks up to orbit is incredibly inefficient. Okay. When we okay, let's uh, first stage, multiple stages of the racket is there, right? First stage always will be there the solid. Okay, when the solid fuel is burned, then the remaining tanks of the our launching body will remain empty, right? When we detach from the main satellite body, that will reduce the weight of the our racket, so it can easily move on the next. But here the keeping, right, the carrying a massive engine structure and empty fuel tank. See, empty fuel tank and engine, that will incredibly inefficient. That will, if we carry that empty tank for moving in next orbits also, then it will be take it will take very time of us, and it will become inefficient. Okay, that is the dead weight penalty. What is the remaining tank and that massive engine structure? Next, what are here? Just scooter analogy. What is the scooter analogy? Okay, let's go to learn it. Attracting two heavy aircraft engine to a lightweight scooter to travel at 40 km per hour only add useless dead weight, killing mileage. The rackets face the same penalty if they don't discard empty structure. Okay, what is that? Attaching two heavy aircraft. Attaching two heavy aircraft engine to a lightweight scooter. Just remember, our lightweight scooter, when we attach it to heavy aircraft engine, okay, to travel at 40 km per hour only adds useless dead weight and killing mileage, right? Okay, adding extra aircraft engine to the lighter scooter, it will kill useless. It will add useless dead weight, and also it will kill the mileage. In the same way, the racket face the same penalty like this if they don't discard empty structure. This dead weight penalty, we don't discard empty space. That is the scooter analogy. Okay, just they compared with the scooter. That's it. There is no anything. Solution one. Oh, what is the solution for that then? That is multi-staging. For to remove the dead weight penalty, they come with the solution by multi-staging racket. The racket engine and tanks are discarded stage by stage as soon as they finish firing. Is constantly drop dead weight, that will constantly drop, not dead weight, that will last the dead weight constantly and saving the tons of fuel also. Okay, in the for example, okay, observe here guys. For example, a PSLV weight is 3 lakh kg at launch. Okay, when we prepared and manufacture the satellite, so satellite not manufacture the rocket. Okay, when we kept the position in the launching site, at that time it's the 3 lakh kg. Still it is on the land only. Okay, the land means earth, but its payload is only, but 3 lakh kg rocket hold the payload is 1500 kg only. Okay, that is 0.5% of the its loss mass. The other 99.5% is purely fuel. Remaining 99.5% is purely fuel in the rocket. Just remember guys, and tanks and structural engine that must be set systematically. They will automatically remove of the system. That is, for example, they are saying, okay, what are some engines will be there in a racket? What are those fuel stages and what are those engines? Let's dive in that. What is the first one? That is solid rocket propulsion, right? That is solid rocket propulsion. Yeah, it is a fuel and it is oxidizer are mixed together. It is fuel and oxidizer mixed together. Both are mixed together. What will and cast into the solid pack like a giant firework. Its crucial rule. What is its crucial rule of solid rocket propulsion? Once we ignite it, it cannot be stopped, restored, and throttled. Okay, its pros. What is that? Its pros. Okay, it is highest thrust density. It has highest thrust density and mechanically simple and reliable. It is very reliable and mechanically simple. The cons. What is zero control and poor maneuverability? Maneuverability. Poor maneuverability and zero control. Second one, guys. Now that is liquid rocket propulsion. What's it? It is also fuel and oxidizer are stored. The fuel and oxidizer are stored in separate tank. Okay, here oxidizer and fuel are both are stored in separate tanks and pumped into combustion chamber. That's it. And its pros, it is controlled. It completely we can control. We can start or stop or throttle and again restart. We can do like this. Com- it is its cons. What is the consequence? Complicated piping. For piping means we are separating fuel and oxidizer. We are separating here, na. We need piping and lower thrust than the solid. That's it. Now it is interesting cryogenic rocket propulsion, guys. Yeah, a specialized and a highly advanced class of liquid engine is it is. It uses the liquid hydrogen as a fuel at minus 250 degrees Celsius and also liquid oxygen as oxidizer at minus 183 degrees Celsius. Just remember guys, here hydrogen is as fuel. Okay, here liquid oxygen as like oxidizer. Just remember, oxygen it is oxidizer, hydrogen as fuel, and we can store it is in very less temperature, that is 180 degree 3 Celsius. Its pros, it ultimately fuel efficiency and highest specific impulse. Here highest specific impulse is also there, and high complex and extremely expensive, difficult to thermal injection. It is very complex and it is very expensive, difficult thermal insulation. Okay, solid has maximum thrust and liquid is the medium and cryogenic has maximum efficiency. Guys, here is the specific impulse. You heard right? Specific impulse here, that is highest specific impulse present in the cryogenic rocket propulsion, right? What is that impulse? Just remember, impulse is the force into time. Okay, the force means what the initial thrust we need, initial thrust, and at the what time it. That's only. Okay, the specific impulse it defines the total impulse delivered per unit mass of propellant consumed. So, and in seconds it represents how long 1 kg of fuel. Just go through this definition, you can get to know the what is the impulse. Represent how long 1 kg of fuel can produce 1 kg of continuous force. Here's some efficiency rule. Efficiency rule that now thrust comparison. The solid thrust is greater than liquid than cryogenic. Okay. Specific impulse comparison. Here specific impulse. Specific impulse is high for cryogenic, then liquid, then solid. Use solid at the last first stage 1 to fight gravity of the pack. Use cryogenic at upper stage. No circularized precise in vacuum. Okay, now comparison table. There is no I what we have read in both three all are there here only. Okay, let's go once. The solid engine. It's propellant fuel. It is solid binder and oxidizer. Also, the liquid engine. First we counter the solid here. No. We can compare. We need to compare here now. Okay, it is solid binder and oxidizer, and it is hydrogen or kerosene, we can propellant fuel, okay, and liquid hydrogen and oxygen. Here thrust output is, for solid it is highest, for cryogenic it is lowest, but for liquid medium. Specific impulse, for solid it is low, for liquid it is better, for cryogenic it is highest. Here restart and throttle, there is no because here no, because solid engine it cannot be a restart and cannot be controlled, okay. Yeah, it can, the liquid engine it can be controlled and it can be throttle or restart. Cryogenic also we can do throttle and restart. Complexity, this for solid engine complex is not, complex is negligible. Here what is extremely, it is very extremely simple, that's, it is very simple, and it is medium, it is extremely high. The fuel storage, easy, it is easy to store, okay, it is moderate and it is extremely difficult, yeah, to store. And optimum stage, it is first stage or booster, and middle stage it is upper and terminal state stages. Now Now, PSLV, that is Polar Satellite Launch Vehicle. It is third generation. Remember, guys, Polar Satellite Launch Vehicle. It is third generation rocket. Okay, it has maximum four stages. Okay, that is solid, liquid, alternative of solid, liquid, and solid, liquid. Like, okay, PSLV. It is alternative of solid, liquid, and solid, liquid. Just remember that solid and liquid. Here liquid it is because engine, just remember it is first liquid in uses. So because engine it is used first liquid, the first liquid engine used by the PSLV, okay. And solid, next liquid here DLPS4 engine for orbit steering. Primary mission plan, sun synchronous polar orbits. Primary mission plan, what is it, is sun synchronous polar orbits for remote sensing and earth mapping, agriculture monitoring. Its primary mission, what is that, this rocket's primary mission is that remote sensing, earth mapping and agriculture monitoring, that's it, guys. And then payload capacity, what's its the payload capacity, 1860 kg to low earth orbit and 1450 kg to geostationary orbit. Okay. Legacy success. What is the happen? What is the success happened yet? It is highly, we can highly trust on this launch vehicle because it workhorse of ISRO, work workhorse of workhorse of ISRO, that is PSLV, and it is completed over its 63 launches with only three failure we have seen yet. And yeah, its famous flights are, that is Mars orbiter mission, Mangalyaan, Navig satellite and Chandrayaan first. Now second one, that is GSLV MK2, geosynchronous satellite launch vehicle, designed to launch medium class communication payload directly into geosynchronous transfer orbit. Okay, it is designed for mid class communication payload directly into geosynchronous transfer orbit. Stage first has, that is solid, and stage second has liquid, stage third has cryogenic. Here solid, liquid, cryogenic for GSLV MK second. Okay, it is the first satellite, first launching vehicle, the GSLV MK second hold the cryogenic engine, and that is also indigenously developed, that is CE 7.5. Okay, and its payload capacity is 2500 kg. Its nickname is the Naughty Boy. Why it is called Naughty Boy? Because in this title early in its program due to multiple consecutive launch failures. It has failed many times. Because of that, they called naughty boy, associated with reserve engineering and complex development of the cryogenic stage, cryogenic engine stage. We need to develop here cryogenic engine stage also. That's why it take multiple failure of initial days of this. Here's some historical context related to the JSLV MK second is there. What is that? Okay, let's go to that. In the 1990s, India negotiated with Russia to import cryogenic technology. Okay, India is negotiated with Russia just to import the cryogenic technology. Okay, but however, what has happened? USA led geopolitics. Here, USA was commanded the mission, that is commanded the technology, that is not technology. Here, geopolitics is there. What is that? The missile technology control regime blocked the technology transfer. It will block the technology transfer. After that, because of this result, this forced Indian scientists at ISRO to work relentlessly for over a decade to indigenous design, test, and master cryogenic engine physics from scratch. Yeah, that's guy. Now, LVM3 launch vehicle Mark 3, formerly GSLV MK second, third, the India's heaviest operational launch vehicle designed to support heavy commercial communication satellite and future future human space flight program. KLVM3. It is advanced satellite of JSLV MK second, and it is here MK third. Okay. It is highly advanced, and it can has the capacity to take human in the space flight. Okay, and it is also three stages, that is solid, liquid, cryogenic. Okay, here cryogenic engine are CE20. They are using CE20 cryogenic engine. Okay, its payload capacity is, that is 4500 kg to geostationary orbit, 8000 kg to the low Earth orbit. Its major future. What is its future? Yeah, right. GSLV MK third was renamed. It's renamed LVM3 to fight a global naming standard. To fight, we kept LVM3 just to fight global naming standards. The plans are currently underway to replace the liquid core second stage with a next generation semi cryogenic engine utilizing liquid oxygen and refined kerosene, boosting geo transfer orbit capacity to 6,000 kg. What you have get, nobody can get. I know. What is that? Just go once again. LVM3 to LVM3 to fit global naming standard. We kept this name to fit for the global standards. That's one. Okay, that's over. And what is the plan currently underway? The underway to replace the liquid core second stage. We have no second stage. That the first stage is the solid, second stage is the liquid. For that liquid core second stage, with the next generation, we have adding semi cryogenic engine. We use the liquid core second stage. We use, instead of liquid, we use semi cryogenic engine. It is for boost geostationary transfer for the 6. It will take the payload capacity 6000 kg, and it's a major milestone, and it is launched Chandrayana 2, also Chandrayana 3, and designated as the official launch vehicle for India's upcoming crewed orbital mission, that is also Gaganyaan. I hope guys, yeah, these are comparison table. Once you pause this video and go through it, that's it. And here these are the points related to the what we have studied above, and they are present in the singles lines only. If you want, go once it can help you very easy. Now guys, satellite communication and orbits part. These are some doubts related space. Let's go with this also. Why doesn't the ionosphere block satellite communication? Why? Ionosphere is very harmful, right? Ionosphere means the last layer of the earth. Ionosphere, it is last layer of our earth. Okay, it has um, ions reaction on that layer. Why it is? Why it will not block the communication of the satellite? Because satellite communication bypasses normal broadcast radio wave. Instead, we use microwave, which passes much higher frequency because satellite has microwave, not radio wave. Radio wave easily react, is easily chemical reaction happen with the ionosphere, but microwave it will not. It will easily surface that ionosphere, and these high frequency microwave bands has in satellite, they easily penetrate the highly ionized gaseous layer. Okay, just remember that is highly ionized gaseous layer and experience negligible reflection and diffraction. There is no reflection, no diffraction. Okay, enable uninterrupted line of sight, unlink and downlink path. Okay, here you can see it is our surface. Just assume this is ionosphere, that is satellite microwave. It easily penetrate this layer, and this is the radio wave bands. Okay, AM radio, right? AM radio, its frequency band is very low frequency. AM band is low frequency. Ionosphere reaction, it is reflected back to the earth. Okay, next short wave, it has high frequency but again it is reflected back to the earth. FM radio, it is very high frequency, mostly passes through, it will passes. Television, ultra high frequency, passes cleanly. Okay, and satellite, it is microwave frequency one. Okay, it easily penetrate. Now, solar storms and satellite, what is the relations between solar storms and satellite? Okay, let's go. Solar storms are a highly energetic event, right? Solar storms are a highly energetic event, means some mass of sun's ejection of some amount of masses out from the sun. That is reaction happening now. That's impact all active satellite globally. Yeah, they do not selectively target. They do not selectively target sun synchronous orbit, right? Solar solar storm discharge massive quantity of charged particle, plasma, and high energy radiation. Solar storm contain charged particle, plasma, and high energy radiation. Okay, what is because, and because of this also, that is solar storm has this charged particle, plasma, high energy radiation. Instead, but still having this energy, how the earth will control from the solar storms? Our planet core create a powerful magnetosphere which act as invisible shield and deflect the bulk of cosmic particles. Only unusual severe coronal mass ejection fires are warp this shield sufficiently to cause severe satellite degradation. Here, our Earth magnetosphere, our Earth has magnetic power. Okay, that magnetic power, with of our Earth magnetic power, we will not able to very harmly effect on the solar storms. Okay. Now, guys, geosynchronous orbit. Okay, I have already done, but okay, let's go once it. Orbit, in which satellite orbital revolution period exact matches the Earth rotational duration on its axis. Okay, it will take exact rotational period of the Earth, like it is also geosynchronous orbit. Okay, some required conditions for there for geosynchronous orbit. For that, the path must be a highly circular, need to be highly circular, and the period is exactly 24 hour will be need. And here altitude 35,786 kilometer above the earth surface. At exactly 35,786 kilometer altitude, the gravitational physics equation resolved to yield an orbital cycle of exactly one sidereal day. Okay, next inclined geosynchronous orbit. That is figure 8. I have explained in the in what I have taken the session for it. And yeah, if the geosynchronous orbit path is inclined at an angle to the equator, yeah, geosynchronous orbit has inclined some angle, the satellite still matches the Earth cycle, meaning it returns to the same longitudinal day, and the ground observer it north and south during the day and tracing the characteristics. It is eightfold path analemma in the sky. A circle is just an ellipse with an both the foci overlapping the center, thus every circular orbit is technically an ellipse too. Okay, geostationary orbit. Here's, you know na, geosynchronous orbit. That's why I'm reading, I'm not explaining here. Here, geostationary orbit, it is zero inclination, but the geosynchronous orbit has some inclined angle, and it will rotate. Its condition is it will rotate from west to east directly over the equator, and satellite remain entirely static to observe on the ground. The antennas, okay, same. The comparison is there. You can read. You can pause the video and you can read if you want. All the geostationary orbits are geosynchronous, but all the geosynchronous orbit are not are geosynchronous. Okay, sorry guys. All geostationary orbit are geosynchronous. Okay, but not all geosynchronous orbits are geostationary. Yeah, it is right. Geostationary visibility limit. Okay, not limits is there. Curvature law. If a geostationary satellite is parked at a longitude directly over Sri Lanka or Africa, the Indian antennas point towards it easily. But what about the satellite parked over South Africa? Okay, what is happening? Here you understand. If a geostationary satellite is parked at a longitude directly over Sri Lanka. Okay, it's parked their longitude directly towards the Sri Lanka or Africa. Okay, just remember, they directly towards the Sri Lanka or Africa. The Indian antenna point towards it easily. But what about a satellite parked over South Africa? South America, not Africa. Okay. When if satellite is parked in the South Africa, what will happen? Absolutely impossible to observe from India. It is impossible to observe from India. Since the satellite is locked at South America's longitude and Earth is an opaque sphere, the Earth itself blocks the line of sight. Because both the turn together, that satellite will remain permanently invisible below the Indian horizon forever. Guys, you can read, you can get. I'm not able to explaining here. I think I need to take some break. I will come back after some time. Now, guys, satellite orbits and privatization. Okay. Oh, okay. What is sun synchronous orbit? You have already known sun synchronous orbit. It is a highly specialized and near polar low Earth orbit. It is present at the low Earth orbit. It is polar. That is polar. Okay, at the near polar low Earth orbit. Defining character: satellite in this orbit always passes over any given geographic point of the Earth's surface at nearly the same local solar time. Same that you have known. Okay, some interesting point is there. We'll read it. Unlike geosynchronous orbit, which lag to the Earth rotation speed, Sun synchronous orbit lag in with the Earth's orbital moment around the Sun. Okay, the Sun synchronous orbit is not like geosynchronous orbit because which lag the Earth rotation speed. Okay, why this is critical for remote sensing? When satellites take images for forest, glacier, and agriculture field over weeks or months, scientists need to compare them to detect match changes. If the angle of the sun changes continuously, shadow would shift and warp. Skewing visual calculation, varying lighting condition would make spectral analysis highly inconsistent. By maintaining a constant solar angle, the satellite captures image with identical shadow profile and reflection level, making scientific comparison highly reliable. Okay, why doesn't the orbit plane remain fixed? Why it is not able to remain fixed? What is happening? Earth is revolving around the sun. Just assume, guys, Earth is revolving around the sun, and Earth move along its elliptical track, right? Obviously, Earth will move around the Sun in an elliptical orbit. The direction of the sunlight continuously shifts over the course of the year. Yeah, direction of the sunlight will varies on the Earth, right? If that's because of that, season will be varied. We can observe the season of, and if the satellite's orbital plane remained entirely fixed in space, then after a couple of months what will be happen? If they are telling, if fixed, entirely fixed, the satellite, we launched the satellite, no, that it will fixed in a space, what will be happen after couple of months or 3 months or 2 months? What will happen? The satellite would cross the equator at completely different local time. For example, we launch the satellite at 2 a.m. and commonly it will cross the equator on first month in 12 p.m. But after 3 months, it may be shift at 2 p.m. That's 2 hour gap will be there. That drift because that the drift will be there in the satellite, but because to competing that, the solution is the oscillating orbital plane. The orbital plane is there now. We have to need to isolate for that. Just 1 degree per day. If we drift the satellite 1 degree per day, it will be complete. The Earth will be rotate around the sun in a 360 angle, right? In the same way, when we per day we rotate 1 degree of the satellite, that that exactly like a, our Earth will round like a round around the sun. In the same way, Earth revolves around the not Earth. Satellite revolve around the Earth. To prevent the drift, the orbit plane itself must slowly turn and gradually axial rotation of the orbit path known as orbital path plane precision. Just we need to keep that plane drift, that is by about 1 degree per day. We have to maintain the drift of satellite like that. Then it will be corrected like our Earth rotations. That's it. Okay, now privatization of Indian space sector. Right? You know, guys, ISRO is performed all function in single-handedly. And also here research and development, structure design, commercial launches, data say, and all policy administration. All these works are done by ISRO itself. So now all these burden, all the work will be lying, all the work will be done by ISRO. It will be felt very burden for ISRO to maintain and to focus more missions like Gaganyaan, Chandrayaan mission, need to deep space mission. Now, because of the privatization in space sector, it helps the divide scientific research and from the commercial operation. Okay, that's it. And what is the core objective? The ISRO of mass assembly burden. So it can be focused strictly on deep space probe, which is Gaganyaan, Chandrayaan, Mangalyaan, and advanced propulsion designs. We reduce the burden of the small launches. Now, New Space India Limited. What is it? It is okay. It is incorporated in March 2019, and it is a fully state owned central public sector enterprises. It is also government body. Okay, guys. And administrative department. It is Department of Space, and ISRO is also government. New Space India Limited is also government. Okay, both are worked under Department of Space. And its major function is New Space India Limited. Major function is commercialization of tech and transfer of manufacturing and demand driven satellite missions also. Do you know commercialization of tech means the spin-off patent? Some patent taken by the ISRO, they are licensed to the now private industries, and some now manufacture. The transfer of manufacture means the making of rocket will be shifted towards the who are privately constructed for space sector. For example, production of PSLV was transferred entirely to the Hindustan Aeronautic Limited Company and Larsen and Turbo. Okay. Next, demand-driven satellite mission here. It is reversing the world space supply model. What is then? What is here world space? Okay, world space supply model. What is that? Means then here what will be happen in world model? ISRO build a satellite. First, ISRO will build satellite and then it will launch and then look for customer. It is old model. But now in the new model, they identify the customer demands first. They identify the demands first. Then gather payment. They will gather payment and then instruct the ISRO or industry to assemble or launch. That's it, guys. And a key commercial launches of the milestone of the this from New India Space Limited company, commercialize foreign and domestic. It will commercialize both foreign also and domestic launches by utilizing LVM3 and PSLV launches. Okay, it is Amazon on Brazil. It is launched at the Brazil and it is first dedicated commercial mission of PSLV for international payload. And just on one web mission also launched by New Space India Limited successfully and executed massive multi-satellite launches on LVM3, showcasing India's commercial capability in heavy orbital deployment. Then now crucial communication satellite is there. CMS 03, GSAT 7R is there, GSAT 11 and GSAT 20, GSAT N2, Bluebird Block 2. And now, yeah, this year 2026 prelims asked based on this IN space the nodal regulator INSPACA. The node it is a nodal regulator. The Indian National Space Promotion and Authorization Center. Its nature it is independent and it is a single window nodal clearance agency operating within Department of Science. It is also operating within Department of Science, but it is independent body. Remember, it is independent body. And why it is created? Why? Like because of the private company entering the space sector, right? Now private company are also entering in the space sector, and then they need permission to build rockets, manufacture satellite, and utilize the ISRO's launch pad also, right? For that, the in space it will serve as the regulator to authorize and supervise their activities. That's it. It will act as a regulator for the private company who want to make any satellite manufacturer due to any launch pad for the and India Space Association. Just guys, remember here, India Indian Space Association. What is that? It is not unlike New Space India Limited and in, in sorry Indian National Space Promotion and Authorization Centers. ISP, Indian Space Association, is not a government body. Just remember, it is ISPA, it is not a government body. It's a private industry collaborative association. Okay, it is a private industry collaborative association of space system manufacturer and acting as a advocacy group to voice private industry concern before policy developer. Similar to NASCOM for IT sector and STAMP for auto sector. I hope you get. And some comparison is there. ISRO is for research and development body nature, and its primary role is the core scientific research and tech development. New Space India Limited. It is also government's public sector undertaking, and it is commercial transaction and marketing of ISRO's assets. IN Space. It is the nodal regulator. It will give a single window licensing and authorization of private firms. And this is Indian Space Association. It is industrial association and represent private players and shape the advocacy topics. Department of Science. Under the Department of Science, ISRO is there, INSPAC is there, and New Space India Limited is there. Now, guys, major missions of our ISRO. Okay, first one, we go into the Aditya L1 mission. Yeah, Aditya L1 is the India's first dedicated solar observation mission. Yes, and it is completely developed by ISRO to the monitor and the study solar behavior continuously. Okay, it will continuously monitor and study solar behavior continuously and position at the specialized Lagrange point L1, and it's approx 1.5 kilometers from the surface. And here, just remember, this is our earth, right? This is our earth and this is our sun, and Lagrange point is there. From earth to sun, the distance is 150 million kilometer. Observe guys, 150 million kilometer. Okay, it's just 1% of this distance. The Lagrange point is there, just 1.5 million kilometer. And from distance to our moon is 3.8 lakh 4 kilometer. That's it. And why L1 point is crucial here? L1 point is crucial because to balance the both the gravitational attraction there, and also so no solar eclipse will directly enter on it. Uninherited observation of the sun without interference from the earth's shadow. If we kept this satellite, if here or here, when sunlight will fall on earth, its shadow will be fall on this satellite now. That's why we don't want this any eclipse here. That's why we kept here. And continuous solar diagnostic enabling early warning vector of coronal mass ejection. It will help to continuously detect what is happening around the sun. And now, better analysis of space weather and also solar magnetic dynamism. Now, guys, enter into the second. It is also related to the Aditya L1, but some here scientific payload that there are 7 payloads there. In that, they are categorized into 2. Okay, first 4 sensor they categorized remote sensing payload, and second group they are categorized in suit payload. The remote sensing payload. In remote sensing payload, the one is okay. They designed to observe the sun directly from the distance. They designed to observe the sun directly. Okay, they directly from the distance. What is here first one? The first one is the visible emission line coronagraph. Okay, visible emission line coronagraph. It studies the solar corona, means outer solar atmosphere. Examine coronal heating mechanism and solar wind origin and coronal mass ejection and acceleration. Okay, it will study all that sun's atmosphere behavior. Okay, that is visible emission line coronagraph. Next, second one, solar ultraviolet imaging telescope. What is that? It analyzes solar ultraviolet radiation profile to map the chromosphere and photosphere dynamics. To map here, just it map the chromosphere and photosphere dynamic. What are the dynamic? What are the fluctuate happening there? Okay, and just remember, solar ultraviolet imaging telescope. It will analyze solar ultraviolet radiation profile. Okay, solar ultraviolet radiation profile to the map. It will map chromosphere to protosphere. Okay, and protosphere. Here, third one is solar low energy X-ray spectrometer. Okay, it will measure low energy X-ray spectrum for detailing energetic solar flares of solar flare energy, how much they will detect or measure by this spectrometer. And high energy L1 orbiting X-ray spectrometer measure hard and high energy X-ray emitted during explosive solar flares. Group B, in situ payloads, 3 sensors there. Okay, they designed to for detect and local measurement of particle reaching to the L1. It will these three in-shoot payload. Just remember, in-shoot payload, 3 sensor will be there. They are designed to detect and local measurement of particle reaching around the Lagrange band. Okay, first one here, Aditya solar wind particle experiment. It measures properties of solar wind particle. Oh, solar winds particle has, that is proton and alpha particles and heavy ion will include. They will study or measure these by using this sensor and plasma analyzer package for Aditya. Here decipher the plasma composition and energetic electron array surrounding Lagrange point. Okay, right. Plasma will be there in the sun, right? Their composition, what are the composition and energetic electron of the surrounding Lagrange point, what is there? They will observe. Third one, advanced triaxial high resolution digital magnetometer. Capture magnetic field profile. It will capture magnetic field profile surrounding the spacecraft, mapping the interplanetary solar magnetism. That's it. Actual point here I want to say you, that is, wait 1 minute. Yeah, no. I said you know Lagrange's point it is kept for a balance in our L1 point. No, that is not the truly perfect because it will not a perfectly stable. It passive gravitational well. It is gravitationally well, but small perturbation can cause the spacecraft to slowly slide away. Because for that solution, it will slowly slide away. Okay, for that solution, on-board fuel reserve are preserved for periodic thruster burns. They don't want to make our satellite to go further. That's why they preserve fuel in that. And if in the satellite is deviate from that path, then they can burn the fuel and again come back to their original position. That will help. This orbital correction keep Aditya L1 as a precision hollow orbit over the L1. Next, next is Chandrayana program. Okay, 1, 2, and 3. You know, guys, right? Here I don't want to go further deeper here. Just I will explain what. Just I will go in a brief. Okay. It is developed by ISRO and PSLV, and it is launched through PSLV and formed an orbiter alongside the Moon Impact Probe. And here, major achievements. It is Chandrayana first, right? Major information is hydroxyl. They identify the hydroxyl molecule OH and water ice significance on the lunar surface, changing the planetary signs. Lava tube here. Image underground lava tubes. These offer natural thermal insulation and radiation protection for future human lunar orbit. And yeah, you know, right? I explained in session. I think around it is fifth session. No, fifth or sixth session. I think so. Okay, now structural evolution. Here Chandrayana 2, Chandrayana 3. What is the difference? The launch vehicle for Chandrayana first is PSLV. You just remember this table, guys, and you can have the ability to try to answer the any questions related to the Chandrayana first 2 3. And if you don't know, then also able to eliminate the options also because of this table only. Okay, just remember what is here. The payload component has Chandrayana that PSLV is launch vehicle. Here orbiter and lunar impact probe is there. Here what is the mission outcome is there. It is completely successful. Yeah, Chandrayana first is completely successful, right? Chandrayana 2, the launch vehicle is LVM3M1. Here the payload components are orbiter and Vikram lander and Pragyan rover is there. Pragyan rover and Vikram lander, but they are partially successful. Lander is crashed. Okay, the lander is crashed. The partially successful orbiter will be succeeded. Chandrayaan 3, LVM3 and M4, the propulsion module, lander, rover, no orbiter. Here there is no orbiter. It is just for propulsion module, lander and rover. It completely successful and we launched the first India is the first country to launch the satellite on the south pole of the moon. That's it. And now, very interesting point. Chandrayana 4, 5 and Gaganyaan. Chandrayana 4 is the lunar sample return. But I will tell here brief, just that brief things here. Okay, what is that? If we launch the satellite, okay, from distinct LVM3 only, we launch the satellite and we need to bring the some sample from the moon. First it propulsion module and then descend. It will land on the moon and then after take from the moon, that is ascender, and then transfer and re-entry the earth atmosphere. What is the Chandrayana 5? That is LUPEX, giant venture. Here giant venture, LUPEX means giant venture. India and JAXA, that is Japan. Both country are ISRO and JAXA. JAXA is the Japan for lunar polar exploration. Okay, therefore it is launching for the lunar polar exploration. It will carry a heavy sophisticated rover. They are around 350 kg to detect and quantify the subsurface water. They will detect and quantify that any subsurface water is there. Now Gaganyaan. It is just remember Gaganyaan means human space flight program. It is. They are designed to send Indian astronaut into the low Earth orbit using a human-rated launch vehicle designed to human launch vehicle mission 3. Okay, the human rating, the structural modification of LVM3 to maximize safety, including an active crew escape system in case of launch anomalies. Okay, crew module here. What is that crew module? Pressurized environmental hosting astronaut service module, unpressurized system providing power, propulsion, and different supporters. Now,